This is the introductory picture. It's a picture of Brian Bellhouse, not a picture of me. I think most of you know me, but just in case, I'm Lionel Tarassenko. I first met Brian on the football field, like a lot of us, when playing for Keble against Magdalen. In those days, Brian was in the first 11. I did play with Brian as well for Magdalen's second 11 when I had a spell as a college lecturer here. I also played against and with Brian at cricket, and I'm sure that's true of a lot of people here. But in fact, my second meeting with Brian was actually when I turned up to his second year fluid mechanics lectures in the late 70s in the Department of Engineering Science. So I was an undergraduate in the late 70s when I met Brian. I then went off to work in industry, came back, and I did do a doctorate in medical engineering, and it was quite rare in those days because I managed to do a doctorate in medical or biomedical engineering without being in the medical engineering unit. And that's because I did it at the John Radcliffe Hospital in the Department of Pediatrics. But soon enough, Brian sort of grabbed me back for the MEU, and I was back in 1986. So I was a research fellow, and I worked part-time at Bellhouse Medical Products with people like Elspeth, who had the desk next to me, and in fact also Brian's wife Elizabeth, who was a stalwart of Bellhouse Medical Products in the early days, and I shall mention that in my own talk. And then I was appointed as a university lecturer 30 years ago in a month's time, a fellow of St. Hugh's, and then was appointed the chair of electrical engineering in 1997, continued to be a colleague of Brian's, and there was a very important meeting that Brian attended that I can remember to this day because actually it was on 9/11. So Brian Bellhouse, Mike Brady and I turned up in the offices of the newly appointed Regius Professor of Medicine, John Bell as he then was, and that's when we had the idea of building on the success of the medical engineering unit in Banbury Road and create the Institute of Biomedical Engineering on the Headington campus. And that was 2001. I knew I was going to have to do the hard yards because Brian was about 3 years away from retirement and Mike Brady was about 8 years away from retirement. But in the end, both Brian and Mike helped with the setting up of the IBME, and we opened 10 years ago. And that building is indeed part of the legacy of Brian's time as a pioneer in medical engineering here in Oxford. So, thank you to all of you for coming. I'm going to try and close that door, or does it shut automatically? If you do shut the door. So we have about 60 people here today. Welcome to the auditorium. We had the idea, in fact, it was Jaime who suggested we should do a scientific symposium in Brian's memory, and it was very easy to find speakers. So there are 9 of us who will reminisce a little bit about Brian and then go on to say how it's influenced what we're doing today. And I will ask everybody to introduce themselves, talk about their connection with Brian, and then talk about their work since they left the medical engineering unit. We've tried to time the speakers so that oldest first and newest collaborators, so 21st century collaborators after tea, 20th century collaborators are before tea. The oldest actually is Ian Serby. I don't know where Ian is sitting over there. So I'm just queue jumping. I should really be second in the talks, but I'm queue jumping as a result of still being in the department where Ian retired a couple of years ago. So there are also a few people, I wanted to say in my introduction, who've not been able to be here, and they have sent tributes to Brian, and I've printed copies of them, certainly for all members of the family, starting with Hugh Millwood. I'll just read one paragraph from Hugh because I think it chimes in with a lot of the things that people have written by email. So this is Hugh Millwood, and he says, Brian's first words to me were, "So, you are a footballer?" I was being interviewed for a place to read engineering science at Magdalen in 1984. I didn't realize it then, but I would be at Brian's side, centre of defence, research in the lab, and university spin-out adventures for the next 15 years. And then he goes on over the next 3 pages to describe that interaction. There are other people, including people from Australia who couldn't be here, but we do have somebody who's flown in all the way from Australia to be with us here today, and that's Mark Kendall. Thank you very much, Mark, for making the effort. You're the furthest travelled speaker today, and we're very grateful. The way we're going to do it is we're going to try and make it informal. I've asked everybody to speak for 15-20 minutes. We can take questions or we can move on to the next speaker. I will move straight on to my talk unless there are any other questions that people want to ask at this stage. No, okay. So, my own reminiscences are to do with a project which had started when I joined the medical engineering unit in 1986, and I was platelet monitoring. And the idea there was to probe some biological cells with light. And what I want to draw in my talk over the next 15 minutes or so is how this idea of probing the body or cells within the body with light has enabled me to have many innovations in the field of medical engineering in the last 30 years or so. So it all begins in the place that we all recognized. So I went on to, this is not a picture that I took when I was at the medical engineering unit in the mid-80s. This is actually on the web. It's still a university building and houses a different department, but I think you will agree it hasn't changed very much since those heady days of the early 80s. And in fact, I believe the 70s when Brian started his work in medical engineering research at the corner between Banbury Road and Bevington Road. And Paul, I do remember opening the door to you when you came for interview. You were coming up those steps there, and the bell rang. Brian was upstairs. I happened to be downstairs, opened the door, and I took you upstairs to wait in the conference room until Brian was ready to see you. So I met him 5 minutes before you met the Bellhouse. So I think that was back in 1989 or... Do you can remember which year it was? 93. Goodness. So 25 years ago. But the building pretty much the same. The technicians holding forth and holding the fort as well, because he was fortified because it was animal work. Downstairs, John Greenford, Roger Lewis, and who's the Gerald Walker was. I should remember Gerald because he only retired from the department at Christmas, and we gave him a gift to mark his 42 years with the department. Anyway, the technicians were downstairs. Various students and postdocs distributed around that building, and Brian's office with Daphne Robinson on the first floor. So the platelet monitor. And how does a novel medical product come together? Well, you need to have an unmet clinical need. In this instance, there's a walk on Sussex Beach. You'd be interested to know whether anybody else from Brian's family remembers the story. It's the story that Brian told me about how he thought about first what the platelet monitor might be like, some knowledge of fluid mechanics. Of course, Brian was very knowledgeable in fluid mechanics. You put all of that together and you get a novel medical product. So what is the unmet clinical need? Well, it's to do with transfusion of platelet concentrates for people who are thrombocytopenic. So thrombocytes is the technical name for platelets, so people who have a shortage of platelets. And also when you have chemotherapy, your platelet count can be knocked for 6. So when that happens, you need platelet transfusions. One of the problems about platelets is when you store them prior to these transfusions is the lifetime of the platelets can be highly variable. It's very difficult to predict whether they're going to last 3 days, 5 days, 7 days. And so there was a need for an instrument that could assess platelet viability non-invasively prior to transfusion. And this is where the walk on the Sussex Beach comes. I'm not sure which beach it was, but the story that Brian told me was about all the litter on the beach, and namely paper plates. Somebody's nodding, so it can't just be me that he told the story. And the paper plates As the wind swept them up, they would start rolling along the beach, and so they're discoid shape. And so Brian thought if you impose the right motion onto these discoid-like objects, platelets, then they would roll along, and then when you stopped imposing that motion, they would flap back as the paper plates did on the beach. At least that's the story, and I can see from one or two people nodding that I wasn't the only one who was told that particular story. So when you then combine that with the fluid mechanics, as I've already hinted, healthy platelets are discoid. So here's a healthy platelet, here's another one. So it's a discoid shape. And of course, just like the discs rolling along the beach, the paper plates, if you superimpose a force motion within a channel, they will orientate themselves and keep on rolling down the channel, particularly close to the boundary layers of the stream. And then if you use a light that you shine through, then you will be able to see when they are rolling along or when they're flapping back. As they age on storage, and this is a mixture here, they become much more spheroid. You can see a few aged platelets here. They're much more spheroid rather than discoid. And of course, if you have a discoid shape, it doesn't matter if you superimpose this force motion on top. As you impose the motion back and forth, it will not change their orientation with respect to the fluid flow. So this led to the platelet monitor on which Brian's wife Elizabeth worked, and indeed the platelet monitor paper has Elizabeth as the first author, and a light beam shown perpendicular to the walls and to the direction of flow. And as you can see, the amount of light coming through will be maximal when healthy platelets are aligned, because the light will be able to shine through, and then as they relax back, they will obscure the light, and you get a trough in the light signal, and then as the piston goes back the other way, you get another peak. The peaks are roughly symmetrical, depending on forward or backward motion, without being exactly the same. And so if you have a pack full of healthy platelets, you have a nice sinusoidal signal with a large peak-to-peak value, and that tells you have healthy platelets. And as the platelets deteriorate over time and change shape, they become spheroid, and that sine wave gradually disappears, and you just have a low-level noisy signal. That is the principle of the platelet monitor, which was a product that was sold by Bellhouse Medical Products in the late 80s. And it allowed me to start my first DPhil student, top right here, Dr. Vivian Lee. And Dr. Vivian Lee was a Rhodes Scholar, and I was only a postdoc initially, so it was jointly supervised with Brian. And then when I was appointed in 1988, Vivian became, Brian handed over to me full-time to supervise, and Vivian has had a very distinguished career after doing, she'd done an engineering degree at MIT, did an Oxford DPhil, then went back to Boston to do an MD in medicine, and rose through the ranks to become the CEO of Utah Health and the Dean of the Faculty of Medicine of the University of Utah, with a $3 billion budget, from which she retired last year. And you know how old you get when your students actually begin to retire before you do. I actually have to say, the first Moreland undergraduates I taught in 1986, the John Leveleys and so on, Richard Dobbs, etc., most of whom went to management consultancy, have all retired, and I'm still at it as a poor academic. So the undergrads have retired, some of the postgraduates have retired, but this was Vivian Lee, my first DPhil student, and still one of the best, 70 students later, nowadays after 30 years. And you can see the sort of equipment one used to have in the MAU those days. So excellent equipment built by John Greenford, Roger Lewis, and Gerald Walker. There's a helium neon laser there that we could shine at varying angles. Here it is shining vertically on top of the platelet solution. And I don't know if any of you realize this is the first computer I bought with engineering science funding. It was an IBM PC, and it had an orange screen. So that's my first computer. Here there was a microscope. You could look through the microscope at the cells, the platelets, the red blood cells, and so on. and this was one of the benches on the ground floor of the medical engineering unit at 43 Banbury Road. So we introduced a second wavelength because often the platelet packs had red blood cell contamination. We did some theoretical work, Tversky's multiple scattering theory, to model light scattering by the platelets, whose shape, remember, changes, light scattering by red blood cells, biconcave discs, and this allowed us in Vivian's DPhil thesis to come up with algorithms to estimate quantitatively the numbers of viable platelets. Whereas the platelet monitor was a red, amber, green type of monitor, we came up with a method to estimate this quantitatively. And here are some of the publications. I just put those up to show the sort of time. We're talking 26, 27 years ago that the papers that we wrote in the late 80s and early 90s came out. And then having got a liking for doing these studies of light probing platelet cells in this case, I started investigating the probing of other cells, the red blood cells, and of course that gives rise to the technique of pulse oximetry, which is a way of measuring the oxygen saturation of your blood non-invasively, depending on how much of the hemoglobin has got oxygen bound to it. In normal conditions, your oxygen saturations will be in the upper 90s because most of the HB will actually be HbO2, and as the O2 is absorbed, you go down to venous oxygen saturation, which is 75% only, and both because the HB and the HbO2 molecules have got different absorption spectra, you're able, with a 2 wavelength measurement, to work out their relative concentrations and hence the oxygen saturation. Anyway, the problem was in the late 80s, and it's still pretty much the case, that there wasn't any theory to relate the red and infrared measurements that one made exactly to the level, to the values of oxygen saturation. The theory had been developed for mixtures of HB and HbO2, and the HB is bound to, and is carried by the red blood cells, and the red blood cells actually scatter light. You can't just treat the solution as a pure absorber. So we constructed this experimental apparatus, and as with many pieces of equipment in the MEU in those days, it had an extracorporeal membrane oxygenator, plenty of those about, and that allowed us to change the concentration through the gas mixer here with nitrogen, oxygen, and carbon dioxide, and to vary the flow, vary the oxygen, and to derive a theoretical method to from working out what the red to infrared ratio was, so the measurement in vitro in this case, in a particular cuvette at a red wavelength of about 805 nanometers and an infrared wavelength of 940 nanometers, work out what the oxygen saturation was. And what you have here, very broadly speaking, is the theory that we developed again from multiple scattering, which is the main line here, and all the experimental data in the little white squares here. And my student, Joost de Kok, was actually my 5th DPhil student by then, and after graduating from the MEU, went off to Australia, had a stellar career running the BCG office in Sydney and Canberra, and as I said, retired 2 years ago, having had a career in management consultancy. But his original time in Oxford, after having done his engineering degree in Cambridge, was spent in the MEU on this particular project. And the very final slide, you can see his hand here, and there is a prototype pulse oximeter that we designed to measure the transmission of the light through the finger. You can see it there in the red and the infrared. Here's the amber screen of the IBM PC from the late 80s. And so we studied all the phenomena that affect light transmission through a body segment such as the finger. I've mentioned the multiple scattering by the red blood cells as the arterial blood flows in and out, the relative concentrations of the reduced and oxygenated forms of the hemoglobin molecule, which is effectively what you're trying to measure to work out oxygen saturation, the changes in blood volume during the cardiac cycle, because most blood vessels expand as blood comes in and then contract again. And of course, you're doing all of this against the venous pressure, And that means that the light is also modulated not just by the cardiac cycle, but also by the respiratory cycle. And we've worked on this pretty much for the last 25 years or so. This is a very recent set of studies that we did with a visiting Italian student up at the IBME, looking this time not at light transmission through the finger, but light reflection from all these various sites in the body. So you can see the sites, and you can see, for example, right at the top on the forehead, if you put a reflectance probe, if you shine a light and measure the reflectance from very close to the LED that shines the light, you get a very nice pulsatile signal in times with a heartbeat. And on top of that, you can also see the respiration. And we have developed over the last decade or so signal quality indices that tell us how good the signal is. And you can see we can rank, you get a very good signal from the ear, nose, forehead, chest, and finger. And you can already see by sight, but these are quantitative methods to rank them. The arm, the neck, and the wrist give you signals which are not as good as from these other sites. And we have, over the last 25 years, developed many applications of this technology for clinical use. I mentioned the work with Joost de Kock. The final chapter of his thesis was actually building the reflectance pulse oximeter into a haptic contact lens to be worn by patients during operations, because when you have a major operation, you tend to get peripheral shutdown, and so you can't really measure the oxygen saturation by putting a probe on the finger. You don't get shut down to the major organs, the brain and the kidney, so we're using the eye as a window to do retinal pulse oximetry. Plenty of work with other students to extract both the heart rate and the respiratory rate from those signals. Some very recent work in the Oxford renal unit to look at the autoregulation of cerebral blood flow during dialysis, the relationship between loss of blood pressure, hypertension, and brain ischemia, lack of oxygen to the brain during hemodialysis, and the loss of cognitive function that people who are on repeated dialysis and keep having these hypertensive episodes experience over a period of time. But I want to finish with the very latest thing that all of this early work in the MEU inspired me to do, which is actually to remove the probe away from the body completely. So what you can do now is take a webcam, for example, the webcam in your smartphone, and actually use it to measure the ambient light that is reflected from exposed skin. So this is work with our collaborator at MIT, Bill Freeman. What you can do is amplify the color changes. So this is an algorithm that actually amplifies the color changes. Everybody, as you're concentrating here and light falls on your faces, every time there's a heartbeat, there's fresh arterial blood that comes through the peripheral vessels, and that blood is slightly more oxygenated than the blood which is just left. And so it's slightly redder than the blood which is returning to the heart via the venous vessels. And these microflushes can be amplified by algorithms, and so you can see at the top there the blood coming in, the blood leaving, next cycle, blood coming, blood leaving. And if this is the reflectance, then you can see there's a dip in reflectance here when it's very red, and then when it's less red, there's a peak here. And this is nothing other than the RGB from the webcam measuring the ambient light reflected from the skin. Of course, from the very modeling, and we are currently using the thesis of Joost de Kock in my research group at the moment, we know it's not just color changes, there are also tiny changes of volume of the peripheral blood vessels which change the amount of ambient light reflected, and again that's in time with the heartbeat. And finally, there's a third effect, which I'm sure Brian would have loved to explain, because it's Newton's third law. To every force, there's an equal and opposite reaction. If you think about it, the blood is coming through your head, through left and right carotids. The head is a solid body, and the blood has nowhere else to go, because it's an enclosed body, and the blood then returns through another path. So every time the blood comes through the carotid, there's a tiny reaction that is set up, and if you sit very, very still, you can actually observe in the person that is sitting still tiny head movements in time with the cardiac frequency. And so even with, as I say, a simple webcam, if you use the right algorithms and if you select regions of interest, if you select them to be quite small from the forehead, you will pick up the breathing signal. So this is 15 seconds. So there's about 3.5 cycles here. And then if you have a much higher resolution, and you use much bigger regions of interest, this is 100 by 100 pixels. This time you can see the individual 1, 2, 3, 4, all the way up to about 17 cardiac cycles in 15 seconds. So that person's heartbeat beating at 68 beats per minute. And so you can measure the breathing rate, you can measure the heart rate, and you can measure also the oxygen saturation. So this is in the physiology lab in this university, part of DPAG, Department of Physiology, Anatomy and Genetics. And you have a subject here who's being filmed. Here's the color chart to make sure that there's no distortion in particular colors. And what we did in the hypoxia lab, we give people different we change the oxygen saturation by changing the concentration of the gases they breathe. If you increase the amount of nitrogen, then you can desaturate somebody quite safely. There's always a doctor present. And so we took about 40 students from the university and did a set of studies a couple of years ago. And we looked at, amongst other things, how the darkness of the skin influences the signal that you measure. But just without going into too much detail, if you look at the reference oxygen saturation, so we desaturate people gradually down to below 80%, then we resaturate them, and then we do a couple of quick oscillations. So this is the reference SpO2, oxygen saturation, and this is the signal from the camera. So what we call the log ratios of ratios are the red and blue signals, and you can see that it changes with the oxygen saturation. You can see the bands and then the two other oscillations. And if you plot the SpO2 versus this quantity extracted from our webcam signal, we get an R squared for this particular volunteer of 0.88. And of course, that's what we did in the lab. The whole idea, as I mentioned, is to take this to the clinic. The clinic in this case is the neonatal intensive care unit. And again, this is what they do in the workshop. So this is the successor to John Greenford, Gerald Walker, and Roger Lewis. Jim Fisk, who I believe actually worked in the MEU for a short time before moving up the hill, built this camera setup. So there's a hole in the top of the incubator here, which allows us with our camera to measure the RGB signal from the ambient light reflected from the baby. So here's baby Ben, a 34-week-old baby, and here are the signals measured from that baby during a 20-minute period. So that baby is 34-week premature, therefore his heart rate, resting heart rate is 170 beats per minute. That's a signal in black from the probe that is on his big toe. And you can see he has a bradycardia here just before T equals 15, recovers, and then another short bradycardia here. In red are the estimates from the webcam. So you can see we track the heart rate pretty well. And in here on this particular plot is the respiratory rate. So it's actually quite difficult to measure the respiratory rate of these babies because their respiratory rate varies from about 25 up to 80, 90. Very fast, shallow breathing because of the immature lungs. And we actually believe, we have a paper in press at the moment where we show that we believe that the camera signal in red is more accurate than the current instrumentation. And finally on the right, what happens is during the bradycardia, the baby desaturates down to below 70% oxygen saturation. And in red, from making a measurement of the ratios of the two wavelength, we can actually find that the camera, the webcam, is able to track the fall in oxygen saturation and the subsequent recovery. And this was a world first when we published it in 2014 with the first group in the world to show that you could use this non-contact measurements to track oxygen saturation in the neonatal intensive care unit. And just to finish off, I will show you a video of doing this in real time. And so this is another baby, again in the Oxford NICU here. We use deep learning algorithms to track the skin of the baby, and that's what you can see here. You have to work out what the skin area is, and that's our deep learning algorithms that do the skin segmentation for the baby. We're now going to switch the baby to a prone position, and what you can see here is the pulsatile signal, which is the computation of the heart rate beating 150 beats per minute from our algorithms, and the respiratory rate is estimated to be 70 beats per minute. And the raw camera signals are up here. Finally, we'll show you that it works under all lighting conditions. This is on a very bright sunny day, and you can still see the heart rate signal here, 159 beats per minute this time, and the respiration signal, the baby is breathing at about 70 beats per minute. And so very clean heart rate and breathing signals with no sensors attached to the baby. That is simply measuring the light reflected from the skin and estimating it at 2 different wavelengths. So finally, my final slide is to summarize what really I learned all these days ago, and which enabled me to have a career in biomedical engineering for the following 30 years. First of all, you identified with your clinical collaborators what the unmet clinical need is. Then you do some in vitro and in vivo experimental work. Brian never forgot that he was a mathematician in the first place, so he's always very keen to insist there should be some theoretical modeling, both analytical, and what we've done a lot more, of course, in the last couple of decades, is computational. And then you carry out the clinical studies with your medical collaborators, the medical researchers, and that's what we do a lot of up in the IBME, because the Institute of Biomedical Engineering, because we're on the medical campus. And then, of course, one other lesson that I've not mentioned here, but was very much part of Brian's ethos, is you should seek to exploit commercially for the benefit of patients. There's no point in just leaving this in the lab. If he had potential to help monitor premature babies, for example, take it out of the lab, set up a spin-out company, or work with a company like Johnson & Johnson, the company that Brian worked with in the 70s, so that the technology can be exploited for patient benefit. And it is very rare to meet one person that can take you from the first bullet point to the bottom bullet point, and Brian was one of those exceptional people, and I'm very grateful for all that I learned in my time in the medical engineering unit. Thank you very much.